Welcome to our class unit today, and we're going to cover earthquake engineering introduction. And I'm Tom Irvine, your instructor, and very happy to have you with us here today. And this is the start of a series of units on earthquake engineering. So we'll just cover some basics today. So this describes the big picture about what earthquake engineering is all about. And the bottom caption shows that earthquake engineering studies how seismic ground motion becomes structural damage, and how buildings can be designed to safely resist this type of excitation. So at the left, we have the earthquake source, and the Earth has these tectonic plates, and these plates try to move relative to one another. They're floating on a partially molten mantle. And the plates get bound up along the interfaces due to frictional effects, and strain energy builds up. And then at some point, the strain energy becomes more than that rocky material can bear, and there's a sudden rupture that causes an earthquake. And that source energy generates various types of seismic waves, and we're going to be talking about body waves and surface waves as we go along. And then that energy, as it propagates to locations where we have our buildings, there's a certain what we call the ground acceleration, and peak ground acceleration, peak ground velocity, and peak ground displacement. And then the building will vibrate in response, and we'll talk about inertial forces, resonance, and vibration modes as we go along. And that resonant behavior can lead to structural dynamics, whether plaster can crack, or we can have other forms of crack occurring in, say, concrete shear walls. We can have beams that undergo plastic deformation and buckling and so forth. So we've got some engineering design guidelines to follow from different codes and standards. And we'll talk quite a bit about those codes and standards. And we also have some mitigation techniques like base isolation and damping that we'll be talking about off and on. So there are different types of magnitude scales, and we're going to have a slide or two on those. And the most common one nowadays is called M sub W, which means a moment magnitude. And here are the major earthquakes, 6.0 and greater MW between 1900 and then 2017. So we'll start at the southern coast of Chile, and then as we go upward along that Pacific coast, you see major earthquakes have happened, and of course Peru and Ecuador, and on into Panama and the Central American countries, up the western edge of Mexico, California, San Andreas Fault, up to the British Columbia, Pacific Coast, Alaska, and then the Aleutian Islands. Then off to the right, the Aleutian Islands, and then meeting up with Japan and Taiwan from China, and then South Korea, and continuing on in Philippines, for example. And then this ring of earthquakes, due to the tectonic plate boundaries, kind of curves around, and New Zealand is a hot spot. And then we have all these countries then, Malaysia and Indonesia and so forth, and Thailand, and then on into Afghanistan, and some of those countries right there in the middle of Asia, and then over to Iran and Iraq, over to Turkey, Greece, Italy, southern Mediterranean, and Caribbean islands as well, like Haiti has earthquakes as well. And there's earthquakes also occurring at various miscellaneous locations. Another place we see earthquakes is associated with volcanoes. So if there's a volcanic eruption, there will be seismic activity as well. That can happen in places like Hawaii, for example. So here's a map of the United States, the 48 states anyways. And off to the left, we see these red lines for the San Andreas Fault going up through California. Now there are major faults like the San Andreas, and then there's also minor fault lines that kind of like branch off from the main fault. And there's also some activity in the eastern edge of California and southern, kind of the southwest of Nevada. The Wasatch Front, Salt Lake City area, upwards to then Wyoming and the Yellowstone National Park, and into Idaho a little bit, and again, upper portion of northwest of Montana. Some activity here in central area of Oklahoma. And this red area here is the New Madrid earthquakes. There was a series that happened of three major earthquakes, 1811, 1812, that actually caused then the Mississippi River to flow backwards. Here's a little area from Chattanooga up towards Knoxville. Here is an area then in the South Carolina. And there's some earthquake activity in Virginia and then upstate New York. And in particular, this plot is showing a 2% probability of exceedance in 50 years based on peak ground acceleration. So peak ground acceleration is the acceleration at given points, whereas the magnitude is representing the energy widespread over an area. More about that as we go along. So let's talk about the seismic waveforms. So there are four basic waveforms, but there are also different hybrid combinations that can happen. We'll start talking about a P wave or primary wave, but a primary wave can turn into a secondary wave and vice versa. And seismologists can look at accelerometer data, accelegrams or seismograms, and they can pick out what kind of waveform is arriving when and what combination it might be. Well, here's the seismic wave, and it is a longitudinal wave. And longitudinal waves are very, very common in nature. So right now you're hearing my voice, and it's a longitudinal wave propagating through the air. There's also the underwater sounds, so whales and dolphins are communicating with one another via longitudinal waveforms underwater. These longitudinal waves can also propagate through wood, through glass, through steel, whatever material you might have, including the body of the earth. So all the layers of dirt, rock, sand, granite, all the layers of the earth. And yeah, the P wave can propagate through those. So if there is a major earthquake, let's say it happens in China, it can be recorded, the energy can be recorded by seismic stations in the United States or Europe or elsewhere, and vice versa, of course. So the P wave is a body wave, and it can also go through the Earth's core. Now, seismologists are really clever, and they have used then these different waveforms that we're starting to talk about to in essence, X-ray the Earth. And yeah, we mentioned P waves can also travel through water. So longitudinal motion, as we mentioned, so alternating compression and then the spraying apart will occur. Now, as this traveling wave energy packet propagates on through, then ideally, then those particles are going to return to their rest position. Well, that may not exactly be true. We may have some Brownian motion going on, and there may be some permanent deformation along the way, but let's just say ideally, if this is behaving in a linear manner, the medium is, then those particles go back to their rest position. So the P wave is the fastest of the four basic seismic waveforms, with a velocity of about 5 to 8 kilometers per second. So those waveforms are traveling very, very fast. Then we have our seismic S waves. Now S stands for shear, or S stands for secondary. Take your pick. And this is also a body wave. And then the disturbance is in a perpendicular direction relative to the propagation vector there. Now S waves do not go through water because water cannot withstand a shear force. So seismologists have noticed something very interesting. These S waves are body waves. They do go through the body of the Earth, but they do not penetrate the core. And that's one of the reasons that geologists have determined that the core of the Earth is partially molten, apparently some type of nickel iron type material. Okay, and S waves are traveling about 60% of the speed of the faster P waves. Okay, the next two waveforms are going to be then the surface waves. So here is the seismic love wave, and it's kind of like the shear wave, only it goes along the surface of the Earth, but it does have this disturbance that's at a perpendicular direction to this velocity vector. These waves do not go through water, and they typically travel from 2 to 6 kilometers per second. So these are surface waves. Now, as far as earthquake engineers are concerned, it's the surface waves that can damage the buildings. But our seismologist cousins are more interested in the body waves, because they just want to learn how the energy is propagating through the body of the Earth and all the layers and so forth, and they're not quite as much interested in what happened along the surface like earthquake engineers are. But of course, there's some overlap there. Seismic Rayleigh waves. Now, these are also surface waves. Pretty interesting waveform. They're very similar to an ocean wave. Like, imagine you're at the beach and it's a nice day and you're seeing those waves roll in. It's kind of like this, but with one key difference. So the water molecules for the ocean wave rolling into the beach has a clockwise motion. But the Rayleigh waves have a counterclockwise, or we call it a retrograde elliptical motion. Interesting. So the motion of the Rayleigh waves, and we mentioned similar to ocean waves, but ocean waves are prograde, Rayleigh waves are retrograde. And there's motion both in the horizontal and vertical axes. And then the typical Rayleigh wave velocity is going to be about 3 kilometers per second. So surface waves propagate slower than do body waves. Take a look at another example here. Now this is going to be a tsunami. This is our tsunami slide. And out in the ocean then, this is a boundary of two plates. And the plate boundaries, there are different sorts depending on geometry and which plate is trying to move in which direction. This is a very common, called a subduction zone. So one plate on the left is tending to go down and to the left, and the other on the right is tending to go upward and to the right. And then that energy, it generates these water waveforms that reach the surface and cause the tsunami. In the open ocean, that tsunami may be traveling 835 kilometers per hour, which is a very fast speed, but with very, very low amplitude. Now, as that energy propagates into the shoreline, two effects happen. There is a vast reduction in the speed, so tsunami waves at the beach are very slow, but they have the waveforms kind of get compressed, bunched up together, and the amplitude gets very high. And you've probably seen then different videos, for example, of on YouTube or elsewhere, of the vast destruction that tsunami waves can cause for buildings and homes and structures near those beach areas. So magnitude scale. So if you hear earthquake has a certain magnitude, you need to stop and ask or try and discern, well, what kind of magnitude is it? Because there's all sorts of magnitudes. So we'll start with the Richter magnitude, M sub L. And these are tailored towards California, by the way. Maximum amplitude recorded by a standard Wood-Anderson seismograph. And then detecting energy around 1 hertz, both body and surface waves. Now, some of these magnitude scales kind of have a upper saturation limit of sorts. So Richter magnitude maybe 6.5 to 7. We've got M sub S. This is a surface wave, particularly attention focused on the Rayleigh surface waves. So waveforms of maybe 20-second period and large shallow earthquakes. Body wave magnitude M sub B, that's based on the P waves and a 1 second period focused on that energy. This is useful for earthquakes and for nuclear test monitoring. Now the most common is moment magnitude, and if you just hear magnitude, it's probably a good assumption that it is a moment magnitude, but it's always good to be precise and get some clarification. So the moment magnitude is calculated from another parameter called a seismic moment, m sub 0, which we'll cover on the next slide. And yeah, there's a derivation from the full waveform spectrum, and this is the modern universal magnitude scale. It does require some analysis to complete that calculation. M sub e is the energy magnitude for radiated seismic energy. Broad spectrum research applications, less commonly reported. There's also a duration magnitude, m sub d, and that's for small local earthquakes. And so for the most part, again, magnitudes are reported as m sub w moment magnitudes. So let's take a closer look at moment magnitude, m sub w, and it's calculated from something called a seismic moment, as we mentioned, m sub 0, which directly results to fault physics. So we have m sub 0 is equal to mu times AD, and mu is the shear modulus of the rock, A is the rupture area, and D is the average slip. So that's the equation for then the moment, seismic moment. Then the moment magnitude, well, we take that m sub 0 and take the log base 10 multiplied by 2 over 3, subtract off 6.07. Now we have our m sub w, and that's the moment magnitude scale. Some more about magnitude scales. So if we have a magnitude of 4, then there might be noticeable shaking of windows and dishes. Small objects may move. Minor damage, very rare. Now, we also have to consider, though, how far away is this location from the epicenter of the earthquake. So we'll talk about the relationship between distance and effects a little bit more detail in an upcoming slide. So for now, let's assume then that these significance, that these are locations nearby the fault. So 5, we have a threshold moment magnitude 5. Structural damage begins to appear, vulnerable buildings, cracks in plaster. 6, significant urban damage is possible. 7, regional structural failures likely, and 8 plus, large-scale infrastructure disruption. So again, we'll say that that is in the vicinity then of the epicenter for that earthquake. So more on magnitude scales. So just showing some fun little cartoon here. So some of these lower magnitudes, then maybe the flower pot on that piece of furniture is just shaking a little bit, and then get up to about 3.5 or so, then shaking a little bit more, get up to about 4.5, then maybe some files or papers are falling off from the desk or out from a drawer. Then we get to 5 and 6, and 5 is threshold for moderate, 6 for strong, 7 for major. Now we're getting damages to houses and structures, and then get past 8, and then we get this really widespread catastrophic damage. So here's some interesting things to think about these magnitude scales. So let's say we've got a 1 unit increase in magnitude. Well, that corresponds to about a 10 times increase in the recorded seismic wave amplitude as measured on a seismograph. And for that same 1 plus magnitude increase, that corresponds to about 32 times more seismic energy released from that source. A little perspective there on how those magnitudes work. Oops, one too many. Let's take a look at the modified Mercalli intensity. Now this is a different type of way to characterize earthquakes, and this is subjective because what are the humans observing and experiencing? So this has nothing to do with instrumentation, it's just human reports, human observations. So the modified Mercalli intensity, if we're down at 1, then the people are not going to feel it, but there may be changes, say, in well water levels, for example. So this may be a large earthquake, but it's so far away to be readily felt by people, but yet does have an effect. Intensity factor 2, a couple of sensitive individuals are going to pick it up. And some delicately suspended objects may swing, like objects on pendulums maybe wind chimes, for example. Get up to 3, felt by several people. Now more people are feeling it. It's kind of like a truck is passing by on the road. More swinging objects. So again, we're under modified Mercalli intensity. Now we're up to 4. Now many people are going to feel it. Dishes are rattling, walls creaking, so forth. Windows rattling. Get up to 5, felt by all. Now people are starting to get a little worried here and concerned. More objects moving around, falling down, falling off shelves. More. We got some cracked plaster, cracked windows, trees and bushes shaking noticeably. Get up to 6. Now more people are getting frightened, and they might feel a bit unsteady on their feet. Even more objects are falling down. Broken plaster, broken windows, damaged chimneys, and so forth. Tree limbs are falling. May start to get some rock falls and landslides and so on. And liquefaction, we'll talk more about liquefaction later on, but if the ground has some high moisture content or a water table underground, then what happens is that the ground's a bit porous, and under the shaking, then there's this like capillary effect, and the water gets drawn up, and that reduces the strength of the soil. It becomes more weakened. And we'll look at some slides later where in Japan a number of years ago there was a earthquake that happened that caused this liquefaction, and some apartment buildings just toppled over. We'll see that later on. Okay, now we go from bad to worse because we're still on the modified Mercalli intensity scale, and we have intensity 7. People are getting really frightened. Some are losing their balance, may trip or so forth. Heavy furniture overturned, that's not good. Now, if the building is built to the latest seismic codes, it's probably going to be okay, but if it's an older building or poorly built, then it may start to have some damage there. And again, chimneys breaking at the roof lines and so forth. And more tree damage and rock falls, liquefaction becoming more severe. Get up to 8, and a lot of people are just going to have a hard time standing at all. Very heavy furniture is moving conspicuously. And if the building is well designed to latest codes, it's going to maybe start to get some slight damage, but not too much. But the anything poorly built or not up to code is probably going to be in very rough shape. And then we get to 9. People are being forcibly thrown to the ground. And then now we're getting considerable damage in buildings, even the ones that were designed to be earthquake resistant. Buildings may shift off foundations if they're not bolted down. And 10 is we're in the catastrophic. And most ordinary masonry structures collapse, damage moderate to severe in many buildings which were designed up to code and to be earthquake resistant. So, yeah, that's your number 10 scale there. A fun little thing. So we're talking earlier about magnitude and how certain damages are expected with certain types of magnitudes, and we'll say that was for the buildings and towns and rather close to the epicenter or fault line. But as we get farther away, then there's distance propagation, so the energy attenuates as it goes through material, and if there's any interfaces due to different layers and so forth. So a bit further away, we may be then for this magnitude 7, we may have a modified Mercalli intensity of 9 with severe, and then a bit further away, then maybe down to 6, and even still further away, then intensity of 3. So again, magnitude is just one number, and it's what's going on in the source. Intensity, though, depends on this distance attenuation. So yeah, how much damage will the structure have? Well, it depends in part on how far away it is from that rupture line, that fault, that epicenter, and so forth. So intensity is the local effects, and magnitude is the energy released. And we're going to be talking about some metrics like peak ground acceleration, for example, that are measured with accelerometers or other seismic instruments, and those are at point sources that measure what's happening at a given location, and heavily dependent, for example, on we call this the soil as well. So there's a whole branch of this we're going to topic called structure-soil interaction. So yeah, the soil effects can amplify energy, and definitely be talking about that. Okay, now here's a children's song. It's kind of a fun little song. It's called "The Wise Man Built His House Upon the Rock." And the context was about the rain coming down and to be built on the bedrock so the house doesn't get washed away, which there's good reason for doing that. But we can also take that kind of advice and apply it to earthquakes, because we like bedrocks. So bedrock is that's what we want to build upon, is bedrock, because it provides earthquake resistance in terms of minimizing seismic wave amplification. So it has a high shear wave velocity, the bedrock does, and stiffness, resulting in low strain amplification. So good idea to build your house upon the bedrock, and as the song goes, that the foolish man built his house upon the sand. We're going to have a lot of fun modeling structures. We are going to get into structural dynamics and the generalized eigenvalue problem, and just all sorts of fun things, modal response spectrum analysis, and so forth. So in the center, we've got this spring mass system. It's a single degree of freedom system. We've got a mass M and a dashpot C. Hooke's law gives us a stiffness K. Then we've got this ground motion, and then the response of the mass. And we'll be doing free body diagrams and derivations and Newton's law, and coming up with governing equations of motion and solving those for different base excitation types from various earthquakes. And this is a good first approximation to model structures, even complex structures like a water tower. Top center, that's the Transamerica Pyramid in San Francisco. And chimneys, smokestacks, even rocket vehicles on the pads, they're like these tall cantilever beams, and if they're being launched from, say, Vandenberg, California, near the San Andreas Fault, then an analysis has to be performed to make sure that that launch vehicle can withstand a potential earthquake, even if it's just going to be on the pad for a week or two prior to launch. Bridges, of course, we'll talk about bridges, cell phone towers, and so forth. So our first approach is model as a single degree of freedom system. Of course, we can model with additional degrees of freedom for greater fidelity, and of course the finite element model, and so forth. So we'll be doing both single degree of freedom models as well as multi-degree of freedom models as we proceed forward in the course series. So let's take a look at resonance. Here's our spring mass system from the previous slide we talked about. Now there's a parameter called the natural frequency. So the natural frequency, there's a couple ways you could think of it. It is the frequency at which a system will vibrate if given an initial displacement and allowed to undergo cycles of free vibration. And it's also the frequency at which an energy exchange is occurring between the potential energy and the kinetic energy. So for our spring mass system on the left, the natural frequency is 1 over 2 pi, and then the square root of stiffness K and mass M. So earthquake engineers like to use natural frequencies, but sometimes earthquake engineers use period, which is the inverse of frequency, and then the seismologists they prefer to use periods. So we're concerned about resonance. Now resonance is the excitation frequency going to excite the natural frequency? We don't want that to happen because that causes dynamic amplification, can lead to failures of various sorts. So resonant dynamic amplification occurs when the excitation frequency is at or near the structure's natural frequency, or equivalently when the excitation period is near the structure's period. Resonance between ground motion and structural frequency drives earthquake damage. Well, structures can be damaged by off-resonant excitation, but we're more particularly concerned about what's going to happen then in the context of resonance, because that's where things can just really get out of hand. So let's take a look at a couple of things here. We have the soil conditions, and what is the dominant energy in the soil, because the soil itself is going to amplify then the energy from those waveforms that we talked about. And then what are the natural frequencies of typical buildings? So whether or not a building gets excited into resonance depends on its own natural frequency and its interaction with the soil and the dominant excitation frequency in the soil. So if we have soft soil, then we have lower frequency from 1 to 2 hertz, where that soil is then amplifying the energy, the arriving energy from all those waveforms, around 1 to 2 hertz. In medium soil, 2 to 4 hertz. Stiff soil, 4 to 8 hertz. And again, bedrock, hard rock, that's what we like, because there's little dynamic amplification going to happen by the soil itself. Now for our buildings, it depends on the height and the construction and so forth. And shorter buildings then have higher natural frequencies, and taller buildings have lower natural frequencies. So if we have a 1 to 2 story wood frame house, then 3.3 to 10 hertz might be its natural frequency. Low rise masonry, 2 to 5 hertz. By the way, what we're most interested in with buildings are the lateral natural frequencies, because buildings tend to be flexible in the lateral axes. Buildings tend to be very stiff and strong in the vertical axis, because the building structure has to support the weight of the building and all of the contents. We're not so much worried about vertical response behavior, but we are concerned about what's going on laterally with these buildings. More about that as we go along. Low-rise masonry, maybe a 2 to 3 story, 2 to 5 hertz. 3 to 5 story steel moment frame, 1.1 to 2.5. 5 to 10. Now RC is reinforced concrete, so shear walls, for example, are made for reinforced concrete. We can also have reinforced concrete moment frame, 0.67 to 1.7 hertz. And then 10 to 20 story steel frame, steel moment frame, 0.33 to 0.83. And 20 to 40 story reinforced concrete shear wall, 0.18 to 0.4. Tall flexible, like 40 plus stories, steel frame, 0.125 to 0.25. And industrial steel braced frame, 1 to 3 stories, 1.7 to 5. So we can take these numbers on the right and then compare them to the numbers on the left and see, for example, is there a likelihood that our building will be excited into resonance. So not all buildings are the same. They all have their individual responses and so forth, and of course that coupled together with the soil. Okay, a couple of metrics here. So these are measurements taken at specific discrete locations and heavily influenced by the soil conditions and the potential for soil amplification. So PGA is the peak ground acceleration. So we take the acceleration time history, the maximum absolute value, report that in G's or meters per second squared. And this controls short period or stiff structures, which would have higher natural frequencies. PGA is often reported in news media. And yes, of these three metrics we'll look at, it's the one that maybe is the most affected by soil amplification. We also have a peak ground velocity, inches per second or centimeters per second, that strongly correlates with structural damage, important for mid-period structures, and related to dynamic stress demand. There's a whole stress velocity relationship that I've got it written in ebook on. I'll try and put that ebook link, make that available to you. Peak ground displacement is a PGD, so the maximum of the displacement time history amplitude, reported in inches or centimeters, that governs long period structures, tall buildings, bridges, and is important in near fault pulse events. There's another metric we're going to get into, and it's going to be called, well, in aerospace, where I kind of come from, it's shock response spectrum. And in the world of earthquake engineering, it's called then the modal response spectrum analysis. And it's another way of then assessing damage potential, and it accounts for the natural frequency or family of natural frequencies that buildings might have at a fixed damping ratio. We'll talk quite a bit about those in future classes. So more fun to look forward to. Here is a slide. It's called intensity. It's the Arias intensity. Excuse me, Arias, or I think it's called Arias intensity. Okay. Let's take the acceleration time history. Let's square it, the amplitude squared, that is. Integrate with respect to time, and then multiply by pi and divide by 2g. And then this is this intensity, I sub a. And this measures the total energy content of the shaking. And it actually has velocity units, although it's not really velocity. And it's useful then for landslides and soil failure assessments. And there's something called a duration by Funak and Brady, d sub 5 minus 95. So this is the time between the 5 and 95% of the cumulative Arias intensity, representing the effective strong motion duration, and important for fatigue and cumulative damage. So this concludes then the part 1 of the introduction, and next time we'll do part 2. So thanks for coming. Hope you have a wonderful day, and I hope to see you again soon. Bye for now.